In general, if I've got e to the something, when I take that derivative, I'm going to end up with e to the something, but we're going to have to remember to do a little bit of chain rule. I have let us know that C1 and C2 are both positive constants, so they're just coming along for the ride when we take the derivative. So when I take this first derivative, I would have C1 e to the negative 3t times negative 3. And then I'll end up with C2 e to the 2t times 2. Totally fine if you want to put those constants out in front. Choice is up to you. When I take the second derivative, almost the same thing is going to happen. I'm just going to be dragging this constant around with me too. So I would have C1 e to the negative 3t, the negative 3 from the first derivative, and then another negative 3 popping out because of chain rule. Same thing over here, C2 e to the 2t, that 2 from the first derivative, and another 2 popping out from chain rule. I'm going to go ahead and just like clean each of those up a little bit. So that first one, I am going to move the constant to the front and make that negative 3 C1 e to the negative 3t plus 2 C2 e to the 2t. And on my second one here, negative 3 times negative 3 will be a positive 9 C1 e to the negative 3t. 2 times 2 is going to leave me with a 4 C2 e to the 2t. Where I'm going with all of this is, as promised, we're going to talk differential equations today. Now, a differential equation just means I have a derivative and an equal sign. We're going to spend a lot of time with differential equations, different types of differential equations, different methods for solving differential equations. But kind of that first section on differential equations and that first homework assignment that you've had on differential equations is actually about verifying that something is a solution, not solving a differential equation. So really, my question is that I want to verify that the y I just listed up there to e to the 2t is a solution to the differential equation, which I'm going to abbreviate as just DE for differential equation. Y double prime plus y prime is equal to 6y. Now, there are lots of different ways to sort of show our work going about verifying that something is a solution. But I think that for me, the easiest way to kind of keep track of what's happening is verifying something as a solution means that I'm going to look at the left-hand side of the equation, and I'm going to look at the right-hand side of the equation. And I'm separately going to work out what those two things are and hope that I get to the same point in the end. So that's the approach that I'm going to take here. So looking at the right-hand side of the equation, this just says, figure out what 6 times y is. So on that right-hand side, well, 6y would be the same as 6 times that whole equation that y is equal to. C1e to the negative 3t plus C2e to the 2t. Not really that exciting. I'm going to go ahead and distribute that out. So 6c1e to the negative 3t plus 6c2e to the 2t. And I'm going to do the same on the left-hand side and show that I'm going to come up with the same answer that we have over here. And that's all it means to verify. So on the left-hand side, I need to take what I got as an answer to y double prime and add that to what I got as an answer to y prime. I'm going to run out of space if I try to put that all in one line. So I'm going to kind of stack them up together. So the y double prime piece was 9c1 e to the negative 3t plus 4c2 e to the 2t. So that's my y double prime. And I'm adding to that y prime. Y prime, negative 3 c1 e to the negative 3t plus 2 c2 e to the 2t. Now, when I add these two things up, I can only add the e to the somethings that match. So that's kind of why I stacked them like this. So if I have 9c1 e to the negative 3t, and I take off 3c1 e to the negative 3t, 6c1 e to the negative 3t remains. If I've got 4c2 e to the 2t plus another 2c2 e to the 2t, I get 6c2 e to the 2t. And then I stand back and I go, oh, hey, look, they match. They're the same. We verified that it is a solution. It is beyond the scope of this course for us to try to solve this differential equation. What the statement of this problem says is I don't have to do that. What I'm being asked to do is to show that if y is equal to this entire equation, then it makes this equation true. So I'm going to start off the same way, and I'm going to think about the left-hand side and the right-hand side. Now this time, there's not really anything to do on the right-hand side. The right-hand side is just secant of x. So what we have to show is that if we plug in the second derivative, we add that to the original function, and we clean up as much of the algebra stuff as we can, it's going to, in the end, be equal to secant of x. So this is the point where I'm going to give everybody a chance to find the first derivative and the second derivative for this whole function, the whole thing. Don't forget the x sine of x hanging off the end. And you're definitely going to need the product rule for this. So just as a reminder, if I have two functions multiplied together, when I take the derivative, I get derivative of the first times the second, plus the first times the derivative of the second. And we're going to need the product rule to get those derivatives. So I'm going to need product rule and I'm going to need chain rule here. So when I look at this first piece, I've got cosine of x times natural log of cosine of x. The derivative of cosine of x is negative sine of x. And then I would leave the natural log cosine x alone. Plus, leave the cosine alone and multiply by the derivative of natural log of cosine. So that's the same as 1 over cosine of x times the derivative of the inside, which is, I'm going to be careful to put in parentheses for my negative sine of x. Now I'm ready for the x times sine of x part, which is another product rule. Derivative of x is 1. So I'll have 1 times sine of x plus leave the x alone and multiply by the derivative of sine, which is cosine of x. There's not a whole lot that we can simplify here, but the one piece that I can definitely do is the cosine of x over cosine of x will cancel. And then this piece is negative sine of x, and I have a positive sine of x. So those will both go away as well. We definitely want to simplify that before we're trying to take the second derivative. So I'm just going to write that a little bit neater. So I have negative sine of x times natural log of cosine x plus x cosine x. And that's what I want to take the second derivative of. So I'm going to have a product rule again. The derivative of negative sine of x would be negative cosine of x times, we're going to leave the ln of cosine x alone, plus we'll leave the negative sine of x alone, and then take the derivative of ln of cosine x. So that would be 1 over cosine x times the derivative of cosine x, which is negative sine of x. Now I'm ready to take my derivative of x cosine x, again using a product rule. So the derivative of x is 1. So I'll have 1 times cosine of x plus x times the derivative of cosine x is negative sine of x. I'm going to pause here and see if there's anything that I can simplify. And I'm not seeing a lot. The one thing that I could do is to take the sine of x, the negative sine of x times negative sine of x, and write that as sine squared. That's an option. But there's not a whole lot I can do with that. So I'm actually going to choose to just kind of leave it alone for a second and see what happens when I try to put this into my differential equation. I didn't give myself nearly enough space on this page, and I'm going to have to flip the page, and I regret that. This is one of those times where I wish I had a tablet with infinitely large paper. Now I'm going to try to squeeze it in. I'm going to end up having to flip the page, but I'm not going to quite flip the page yet. So here's my second derivative. The left-hand side of my differential equation says, take the answer you got for the second derivative and add it to the original y function. So I'm going to go ahead and add in that original y function, and I'm going to do it hopefully in a different color that'll sort of show up. And so here's my y function hiding up in here. So I'm going to add in cosine x times natural log of cosine x. And I'm going to add in x times sine x. And the reason I've done it the way that I did is because conveniently these parts are going to simplify. So when I take that y double prime and I add in what y equals, these parts will cancel out. These parts will cancel out, and I'm just going to be left with this part in the middle. That's the part that I'm going to write on my next page. So we took y double prime and we added in y. Some stuff canceled out, and we were left with negative sine of x times 1 over cosine of x times negative sine of x plus cosine of x. And all the other stuff canceled out. Now we were supposed to show that this equaled secant of x, and it almost does. We just have to work a little bit of trig and fraction magic. So now is the place where I'm going to say negative sine times another negative sine would be a positive sine squared x over cosine of x. And I'm going to go ahead and get a common denominator. And I'm going to take that cosine of x and multiply the top and the bottom by cosine of x. Doing this, my numerator becomes sine squared x plus cosine squared x. And that common denominator was a cosine of x. If you only memorize one trig identity, this has to be it. What is sine squared x plus cosine squared x equal to? You don't have a choice. No one's ever going to give you that one on a test. You have to have it memorized. 1 over cosine has another name, and that other name is secant of x. And we've now verified that that original y value was a solution to the terrible differential equation. Questions about that before I talk a little bit about classifying differential equations, like using some words to classify differential equations? This was messy, but we made it through. Okay. As we develop our toolkit for how to deal with differential equations, we're going to have different techniques depending on the type of differential equation that we're looking at. And so in this part of the book, our textbook gives us a couple of vocabulary words for differential equations. And so we kind of put them into the categories of autonomous, pure time, and non-autonomous. And I will say there are some differential equations that fit both of these buckets. But let's talk a little bit about how we can quickly classify a differential equation. Let's see, there's a question about what's on the quiz for those of you that have the Thursday quiz. And today's quiz does go through homework 11, and homework 11 definitely has verifying something is a differential equation. Homework 11 doesn't have like solve the differential equation except for one pure time differential. But I think you will definitely have to verify that something is a differential equation. Might not be quite as messy as that last one I gave you. The ones on the homework aren't quite that messy, but there are definitely trig and things that involve product rule. So yeah. And all of the questions seem to ask you to categorize whether it's like which of these types. So I would expect that to be on the quiz as well, having to decide. So it's actually pretty straightforward once we know what's going on with these definitions to decide if something is autonomous, pure time, or non-autonomous. Someone pick a letter, any letter except D. No D as in dog. Anything else? G, you got it. So if I had a differential equation that looked like D, I need another letter, not another D. L, M, you got it. So if I had a differential equation that looked like DG, DM equals some stuff. If the stuff over here has only G's in it, because G was the letter in the numerator, that's autonomous, because that differential equation only uses the letter that's in the numerator. If I had DGDM, and it only uses the letter in the denominator, then we call it pure time. And anything that has both is non-autonomous. Now, there are other ways that we can categorize differential equations. We can talk about them being separable. So both autonomous differential equations and pure time differential equations are also always separable. Non-autonomous equations are separable if they can be written as something that only includes the numerator times something that only includes the denominator. We're not going to get to that stuff until the end of the chapter. I just wanted to let you know that there are more vocabulary words coming. For now, these are kind of the three buckets that we're putting problems into. So that said, I had some requests by email to look at a couple of the homework problems. So I wanted to do that and then talk a little bit about the stuff you saw in class yesterday. Because the stuff you saw in class yesterday is genuinely my favorite part of 17B. Yeah.
So when we're looking at the identifying the autonomous, pure-time, and non-autonomous, that's for the actual function or the derivative?
It's for whatever they give us as the differential equation. So let's revisit so let's take a look at, let's just have some more examples here. So if I gave you the differential equation, dy dt equals three t squared minus 5t to the fourth. This is a differential equation because it has a derivative and an equal sign. If we're looking at this, what type of differential equation is it? So really it comes down to, I look at the numerator, I look at the denominator, which one of those variables is in it? Since the denominator is what's in there, this one's going to be pure time. If I had dy dx equals 3y times 1 minus y over 2. Autonomous, pure time, non-autonomous, what's this thing? Because it only uses the variable that's in the numerator. Yeah.
So that would be like for the function that we have to verify for.
So for both of these, I haven't actually given you the function to verify. When we're talking about these classifications, they're with respect to the differential equation. So they're the thing that has a derivative in it. So let's take a look at the previous problem. Well, I guess I'll just come back here. So I know it got a little messy on the page, so let me just try to like make it look less messy. So let's say that this is the thing that we were concerned about. And I'm going to ask you to verify, but also if I asked, what type of differential equation is this? The thing that we should be looking at to determine the type of differential equation is I have to find the thing that has a derivative in it. And I'm going to focus on the thing that has a derivative in it. And maybe in my head, I'm going to have to rearrange that so it looks like the derivative thing equals some stuff. Autonomous, pure time, or non-autonomous? Totally. This one is non-autonomous because if I looked at this, I could rearrange that to say y double prime is equal to secant of x minus y. So I'd have both x's and y's in the differential equation. It doesn't matter at all what the possible solution looks like. I only focus on the differential equation to answer that question about
Or the one like that, the one with
the first one.
yeah.
So yeah, so let's take a minute to look at that at the first one. So for that first one,
So does it matter which one you guys put to the right side? Or the second derivative?
oh, that's a good question. Does it matter which one I deal with, first derivative or second derivative? Because this has both, it's probably best to leave them both where they are. So that I've got derivative stuff equals something.
So
It is autonomous because my derivative stuff is equal to something with only the y's, right? And I didn't write that y prime as dy dt. It's implied that the y prime is dy dt. Talk about average value of a function. If I give you a list of numbers, how do you find the average? I'm going to give you a list of 8 numbers. How would you find the average? Totally. Add them and divide by 8. And why 8? Because it's the number of numbers. Well, really an integral is just a way to add things up. So if I want to find the average value of a function, f of x, on the interval from, let's say, 0 to 6, then I'm going to apply that same idea that I'm going to add them up. And divide by the number of numbers. But what that looks like calculus style, the add them up part means I'm going to add up using an integral all of our values of f of x, and dividing by the number of numbers means dividing by the width of this interval. It really is a formula, but it's probably a formula you already have memorized if you just don't think too hard and say it in words out loud. That I add them all up and I divide by how many numbers there were. Because that's how we find an average. So there are a couple of homework problems on problem set 9 that involve average value. The other request from problem set 9 was to finish problem 2 off and actually like do the integration part. And I think maybe it was more like getting lost in the values for sine and cosine. So I'm not going to redo the whole problem, but I'm going to start off where we ended on Tuesday. So again, this is homework set 9, number 2. And we got to 0 to pi over 6 cosine of x minus sine of 2x dx plus pi over 6 to pi over 2 sine of 2x minus cosine x dx. I'm going to do this pretty quickly, but when I find that antiderivative, I'm asking myself whose derivative is equal to positive cosine. That's positive sine. I don't know why I'm writing cosine. The antiderivative of positive cosine is positive sine of x. The antiderivative of negative sign of something is positive cosine of the something. And I have to remember to divide by 2 because I'm sort of undoing that chain rule part. And all of this is getting evaluated from 0 to pi over 6. So if I plug in, I know I've got another integral to do. Don't worry, I won't skip it. So if I plug in pi over 6, sine of pi over 6 is the value that we're supposed to have memorized. If we don't have it memorized, the time has come. We really need to get the nice numbers for sine, cosine, tangent down. But I come back to my equilateral triangle where the sides are 2. So when I cut them in half, the side is 1. I know that angle is pi over 3. And the one up top here is pi over 6. So if I need to know sine of pi over 6, I grab that pi over 6 angle and I'm looking for the opposite over the hypotenuse. So sine of pi over 6 is equal to 1/2. Cosine, when I plug in pi over 6, 2 times pi over 6 will be pi over 3. Cosine of pi over 3 is 1/2. And that's divided by 2. And now I can plug in my zeros. Sine of 0 is 0. Cosine of 0 is 1. That's that part. Now I'll go do the other portion. So my other integral, if I'm asking myself whose derivative is a positive sign, that's going to be a negative cosine. And I'm going to have to divide by 2 to sort of correct for that chain rule part. That whose derivative is negative cosine, that's negative sine of x. And we're going from pi over 6 to pi over 2. So I'm going to plug in the pi over 2. And when I plug in pi over 2, 2 times pi over 2 is pi. And cosine of pi is -1. So I've got a negative and then -1 over 2 minus sine of pi over 2 is 1. Now I'm going to subtract off plugging in the pi over 6. When I plug in pi over 6, 2 times pi over 6 brings me to pi over 3. And cosine of pi over 3 is 1/2. So this will look like negative 1/2 over 2 minus sine of pi over 6 is 1/2. Yeah, it's a bunch of fractions, but they're not too bad. And if we go ahead and actually simplify that down to a number, which by the way, on a quiz, I really would just walk away at this point and make sure that you get points on that next question, right? If this takes you a minute to simplify, that's a minute you didn't get to spend thinking about how to approach another problem. So I would stop there. But if we finish it off, this looks like 1/2 plus 1/4 minus 1/2. That's a positive 1/2 minus 1. So overall, that's a minus 1/2. That's a 1/4. But if I distribute my minus sign in, that's plus 1/4. Distributing the minus sign in, that's plus 1/2. And I think all my 1/2s cancel out. And I just end up with a 4th plus a 4th. Woo! Good times. I'm going to go ahead and get a picture going. And I know what x cubed looks like. And I know what y equals x looks like. So technically there are two bounded regions, but this part right here, saying we're only going to consider the portion where x is greater than or equal to 0, means I'm only considering this part. That's the portion that I am revolving around the x-axis. So the first thing that I want to do is to look at that and say, when I spin it, am I revolving around one of the sides of the object? And I'm not. So that means that when I go to find the volume, this is going to be a pi big R squared minus a pi little r squared. The next piece is I'm revolving around the x-axis. So I know these should both be dx. So there's my arbitrary cross section. And for my arbitrary cross section, my smaller radius, I'm going to get by starting at the axis of rotation and going until I hit the first part of my arbitrary cross section. And so that curve that we hit is x cubed. For my outer radius, I start at the axis of rotation and I go until I hit the far side. And on that far side, my function is x. So I'd have x squared dx. Partial credit, just for getting that far. But really the question I was asked was, how do you find the bounds? In this case, because I know that I'm looking for the region bounded by these two functions, I'm going to find the bounds by setting the functions equal to each other and figuring out where they intersect. You might be able to just look at those and know that they intersect at 0 and 1. But if you wanted to do algebra to find the 0 and 1, I would be setting x cubed equal to x. And personally, I would move everything to one side so that I can factor. And that's where I would get the +1, the -1. And that's where I would know that there actually are 3 points of intersection. But because he specified that we're only going to take the part where x is greater than or equal to 0, I'm not worrying about the -1 piece. I'm going to give us, I'm going to allocate 10 minutes right now. If there are other questions from homeworks 10 or 11. Yeah. So 3 is the one where we've got the 3 different, drug models. Okay. So I'm going to answer a question from the chat first, and then we'll take a look at 3 from homework 11. So the question is where these equations came from in the first place. So we have 2 kinds of volumes that we're working with in 17B. One is if somewhere in the problem, it uses the word cross-section. This does not use the word cross-section. The other type of volumes that we have include the word revolve, revolving, revolved, but somehow we're talking about revolution. That means we're going to have the area of a circle times the thickness every time. The only difference with the volume of revolution is whether we have an outer radius and an inner radius, or if it's just a single piece. But if it says revolve, revolving, revolved around, this is always going to be my starting point for the equation. Okay. I'm going to take a look at homework 11, number 3. Now there's a lot going on in this problem. Haley, was there a specific part of it that you, or just didn't know where to get started? So, and let me just, no, I will leave it here. Okay, sorry, trying to. So there are 3 different differential equation. Well, there are actually more than 3 models, but here are the 3 models that we are presented with in number 3. We've got the 0 order kinetic model. This is what we've got going on in 3A. In 3B, we've got a model that looks like this. And in 3C, we've got a model that looks like this. Okay, so let's just quickly run through classifying each of these differential equations. It is important to know that in this entire problem, we are told things. We are told that K is a positive constant. We weren't told what the constant was. We're just told that it is a positive constant. We also know that, oh, you know, I wrote this wrong. That's why it wasn't making sense. B is the exponent. K is a positive constant for all of them. In B, we also know that YS is a positive constant. And in part C, we also know that B is a positive constant. So let's take a minute to classify these things. So if I look at part A, the only variables that matter in determining whether it is autonomous or pure time is what's in the numerator and denominator of the derivative. My derivative numerator is y. My derivative denominator is t. There's no y, there's no t. This is just a constant. A is a little bit tricky because this is both autonomous and pure time. Because technically, if I just have like the number 3, y equals 3 is technically a function. X equals 3 is also technically a function. So this is the most confusing one because this one is actually, we could call it both pure time and autonomous. If I look at B, K is a constant, YS is a constant. So really the Y is the only thing I should be looking at. So this is autonomous because it only uses the letter that's in the numerator of the derivative. The bottom one is non-autonomous because I have both a Y and a T in it. Anything that's a constant doesn't particularly matter. Not in terms of classifying what type of differential equation it is. Now for the first one, where it says like state in words what this means. So if I just read this as words, that derivative I read as the change in y over time is equal to a constant. Now, what did y mean in the context of the problem? The rate of change in the concentration of the drug over time is constant. That's it. That's all it means to write that in words. This one says the rate of change in the concentration over time is proportional to the difference between the current concentration and ys. I don't remember what ys stands for in this particular equation, but if I were like writing that in words, he didn't ask us to write that one in words. It's okay. He only asked us to write the first one in words. What you have to do for B and C is the same kind of thing we started the day with, where we're just verifying that something is a solution. You are not being expected to solve either of these at this time. You will be by the end of the chapter. But for right now, we're just verifying that something is a solution. Did that help? Cool. Got another question in the chat. So there was a request to actually write down the words I said for A. So if I were writing this, we would say that the rate of change in concentration over time is constant. Or I could say equal to a constant.